This will be video 3 for section 4.6 on related rates. We're picking it up on problem number 13. Number 13 is talking about we have a 13-foot ladder that's leaning against a house, and then the base starts to slide away. And it says by the time the base is 12 feet, so again, this is not a constant 12, this just happens to be when we're going to look at this. So when that's 12 feet, alright, 12 feet, the base is changing at a rate of 5 feet per second. So this length is getting bigger. Let's call this base. We'll call this height. The ladder is constant 13. So they're telling us that dB dt is equal to 5 feet per second. And again, it's going to be positive feet per second because B is getting larger. And part A says how fast is the top of the ladder sliding down the wall at that moment. So that would be looking for how h is getting smaller. So they're looking for dH dt. Okay, so I need to find a way to relate B and H. And again, it looks like we have the Pythagorean theorem. So this is all for, it looks like, part A. So A continued up here. So it looks like I've got h squared plus 12 squared equals 13 squared. Let's just confirm this. 169. So that means I just made a major blunder. Backing up. Okay, one major mistake I just made because my mind was wandering is that everything's in motion, so I'm writing an equation with that in mind. So h is in motion, so h is still h. B is in motion, so B has to stay B. 13 is not changing. 13 is 13. So we can go ahead and say 13 squared, or 169. So now we want to find information about h and b, and we have an equation that just has h and b. So if I take the derivative, 2h dH dt plus 2b dB dt equals 0. So plugging what I know the base, I know dB dt. I'm looking for dH dt, and so I need to know h. I don't know h, but I do know that it's going to fit within the Pythagorean theorem, and I can solve for h at this specific time. So that means I've got plugging in the 12 like I tried to do earlier. I get 144, so I get 169 minus 144 is 25, which makes h 5. Alright, so now I can plug in 2 times 5, so I've got 10 dH dt plus 2 times b, which is 24, times dB dt, so I've got plus 24 times 5 equals 0. So 5 times 24 is going to be 120, I believe. So I've got 10 dH dt. Let's move that to the other side. I get negative 120. And I get dH dt equals negative 12 once I divide. And negative 12 what? Feet per second. So at that specific moment in time, we're losing about 12 feet per second. So that's dropping pretty fast at this point. So part B wants me to take a look at it again, and it says at what rate is the area changing? So part B, we have area equals 1/2 base times height. Both base and height are in motion, so both need to stay as variables. So I get dA dt equals, looks like quotient or product rule, 1/2 dB dt. So the derivative of the first times the second plus the first, half b, times dH dt. So now I've got dB dt, I'm looking for dA dt, and I've got dH dt. Now, this will work fine because in part A, I found dH dt. So now I can write an equation that includes an h and take its derivative that gives dH dt, and it won't cause me an issue. Had we not gone through this process first, then we probably would have been a little bit slowed down by having this dH dt in our problem. As it stands, all we have to do is plug in what we know and solve, and I'll let you finish that. So then part C, now it talks about angle theta. And it says, how is angle theta and the ground changing at that moment? So part C, it's asking about d theta dt. So I'm going to write an equation that relates theta with everything else I've got going on. And I can do this in lots of ways because I have now lots more information. Okay, so I think I want to use sine. So I'm going to say sine of theta equals adjacent, which is b, over hypotenuse, which is 13. And so we've related theta to b and 13. So now when I take the derivative of this, the derivative of sine of theta, cosine of theta, d theta dt equals 1/13 dB dt. Plug in everything I know, and that would be, I know dB dt is 5. So I have 1/13 times 5 equals d theta dt is what I'm looking for. And then I need a cosine of theta. So mostly, most of the time when I think about finding the cosine of theta, I think about finding out what theta is and then figuring out what the cosine is. But really, I could look at cosine of theta as the thing I want to know, which I should be able to find without ever... crap, I made a mistake, didn't I? Okay. We're 8 minutes into this, so I'm not going to start over. I'm going to go back and fix my mistake. My mistake is that I said sine of theta is b over 13. But really, it would be h over 13. So I'm just going to fix what's going on over here. Some of you probably picked it up a few minutes ago and were screaming at the screen that I was wrong. I heard you finally. Sine of theta is equal to h over 13. So the derivative of sine of theta is cosine theta d theta dt, and 1/13 dh dt. 1/13 dh dt is -12. And now we're back to where I was at a second ago, which is, I don't necessarily need to know theta, I just need to know cosine of theta. And at this moment in time, the cosine of theta is the adjacent over the opposite, or I'm sorry, adjacent over the hypotenuse, which is 12/13. So now when I multiply by this, I get d theta dt. Multiply both sides by 13/12 to cancel this out. And I get the 13s cancel, I get the 12s to cancel, leaving me with -1. -1 what? This is the rate of change of theta. Theta is being measured in radians. So -1 radians per minute, per second. Okay, let's move on to number 16. Actually, let's stop this video because it's at 10 minutes already, and 16 looks like it'll take a little bit of time. So we'll pick it up on video 4 with number 16.